This podcast is brought to you by Triple Automation. So I want you to imagine you're standing right in the middle of a high-volume food processing plant.
Oh, yeah. So it's loud, it's wet, totally chaotic.
Exactly. The air smells like industrial sanitizers, and workers are actively hosing down machinery with these really caustic chemicals.
All right, a harsh environment.
Yeah, and now imagine taking a highly sophisticated robotic arm like the exact kind of ultra-precise technology built to compound volatile pharmaceuticals in a pristine, climate-controlled lab.
Okay, I see where this is going.
You take that pristine lab robot and drop it right into the middle of that wet, gritty, high-pressure assembly line.
It sounds like a disaster waiting to happen, honestly.
Right. But if you are reading our source material today, this article titled Clinical Precision on the Industrial Floor, you know that scenario isn't science fiction at all.
No, it's not. It's actually a very real and pretty unexpected crossover happening in the automation industry right now.
It really is. And our mission for this deep dive today is to figure out why. Why are these ultra-precise medical-grade robotics suddenly showing up on everyday manufacturing floors, and how are they fundamentally future-proofing these businesses?
Well, it forces us to completely rethink the standard industrial playbook,
Yeah.
Like when we visualize high-stakes clinical environments, say a surgical suite or an infectious disease testing lab,
Yep.
we're looking at ecosystems engineered for absolute perfection.
Right. Totally controlled.
Exactly. In those spaces, a fraction of a millimeter mistake or just a single microscopic contaminant doesn't just mean you have a defective product. I mean, it means catastrophic failure. There is zero tolerance for error.
Zero.
Yeah. So the premise we're exploring today asks this really provocative question. What happens when you extract that clinical obsession with zero tolerance perfection and hand it over to a traditional manufacturer producing, like consumer electronics or packaged goods?
Well, you completely alter the physics of the factory floor, right? Starting with the physical footprint itself. Because before you can even talk about upgrading throughput or software, you have to deal with the most stubborn constraint in any industrial layout.
Which is space and, well, human safety.
Exactly. Historically, traditional heavy robotics and human workers just do not mix.
Precisely. The legacy philosophy of industrial engineering assumes that heavy machinery is inherently blind and dangerous.
So the solution has always been isolation.
Right. You build a formidable physical perimeter, like a massive steel safety cage around the equipment, just to keep the fragile human workforce out of the strike zone.
Okay, let's unpack this because our sources highlight specific clinical-grade hardware facilitating this shift, namely systems like the JKS series and the ultra-compact minicab.
Yeah, those are prime examples.
And because these systems were designed for medical and laboratory settings, they carry incredibly strict clinical-grade certifications, right?
Which is a game changer.
They are legally and mechanically cleared to operate in highly sensitive workflows while maintaining, extremely close physical proximity to human technicians.
Which you just couldn't do with traditional bots.
No, not at all. So when you port that clinical grade certification over to a general industrial setting, you are suddenly deploying a system engineered to the highest global standards of human-robot collaboration. You bypass that old safety paradigm entirely.
You really do.
It's like taking a highly trained surgical assistant and putting them on a busy assembly line. You don't need to lock them in a cage to keep everyone safe. But does this mean the traditional, intimidating robot cage taking up half the warehouse is becoming totally obsolete?
Well, what's fascinating here is the underlying mechanical reality of how these senseless systems actually work. It's not a matter of simply, strapping an external LiDAR sensor or a camera onto an old legacy robot.
Well, right. It's built in.
Exactly. The safety mechanisms are intrinsically woven into the physics of the machine itself. Systems like the JKS series, they utilize these advanced torque feedback loops and high-resolution joint sensors.
So they basically feel their own movement.
Yeah, they're constantly calculating their own momentum, inertia, and the exact amount of force required to move a payload. If the arm encounters an unexpected resistance, even something as slight as bumping a human worker's shoulder, the spike in torque data triggers an algorithmic momentum halt in milliseconds.
Wow. So instead of a crude external boundary stopping the machine has an internal real-time awareness of its own physical force.
Exactly.
If it feels an anomaly, the software just cuts the kinetic energy instantly.
It does. Because these systems were born in environments where humans and machines must collaboratively handle delicate tasks. Think about holding a biohazard sample while a technician caps a vial.
Right, you can't have the machine just swinging wildly in that scenario.
No, absolutely not. Safety isn't a bolted-on afterthought. It is the core operating system. So to your question about the obsolescence of the robot cage, yes, for a vast majority of assembly tasks, the era of the steel perimeter is closing.
That's wild to think about.
We are transitioning from isolating dangerous machines to deploying inherently safe, fenceless collaboration. And, if you're running a factory, real estate is one of your highest fixed costs.
Oh, absolutely. Floor space is premium.
So reclaiming thousands of square feet of floor space without compromising an ounce of workforce security, it completely changes the ROI of an automation upgrade.
I want to push back on something here, though. We've established they don't need cages, which means they are operating out in the open, shoulder to shoulder with the workforce.
Right.
But a sterile pharmaceutical lab and a standard gritty factory floor have wildly different environmental stresses.
Oh, for sure. Day and night.
A lab is climate-controlled and pristine. A chemical handling facility or a consumer goods plant is chaotic. Normally, if you hear clinical or laboratory tech, you'd assume it's delicate, maybe even fragile.
Yeah, like a microscope that requires calibration if you just bump it.
Exactly.
Yeah.
But this sounds like it's actually tougher and more rugged than standard heavy industrial gear. How does a machine built for a clean room not just short circuit when a worker blasts it with a high-pressure hose on a Friday afternoon washdown?
Well, it is entirely counterintuitive until you examine what sterility actually demands from an engineering perspective.
Okay, what do you mean?
Extreme cleanliness actually requires extreme durability.
Right.
In a clinical lab, equipment is subjected to incredibly harsh realities to prevent contamination.
Like heavy cleaning.
Oh yeah, we are talking about aggressive chemical disinfectants, peracetic acid, vaporized hydrogen peroxide, and just relentless repeated sanitization cycles.
Wow. Okay, yeah, that is harsh.
A machine cannot survive that if it has, exposed fasteners, standard rubber seals, or porous metallic surfaces where bacteria can hide or chemicals can pool.
That makes perfect sense. To be sterile, you have to be essentially impervious to your environment.
Correct. The sources detail how systems like the JKS series are engineered specifically for these brutal sterilization protocols. They utilize specialized non-porous fluoropolymers.
Fluoropolymers, okay.
Yeah, and they feature exceptionally high ingress protection or IP ratings. The joints are basically hermetically sealed. Often, the internal cavities actually maintain a slight positive pressure.
Wait, positive pressure, what does that do?
It means the air inside the robotic arm is pushing outward. So if a seal were to be hit with a high-pressure jet of liquid, the internal pressure pushes back.
God, that's clever.
Yeah, it prevents microscopic dust or caustic liquids from entering the mechanical housing.
Applying that to the general manufacturing sector is brilliant. Let's go back to that food processing plant example from the start.
Right, the washdown scenario.
Yeah, they undergo intense daily washdown procedures. They are spraying down conveyors with caustic foam to prevent salmonella or listeria. Standard industrial automation really struggles in that environment.
It does. The chemical agents eat away at the polyurethane seals, moisture gets into the gearboxes, and the hardware just slowly rusts from the inside out.
Which leads to catastrophic downtime.
Exactly. But by strategically deploying laboratory-grade hardware on that food processing line, you are essentially immunizing your operation against its most challenging environmental factors.
Because it's already built for the harsh lab cleaning.
Right. The crossover works because the engineering solution for extreme clinical sterility, sealed, non-porous, chemically resistant housing, turns out to be the exact same solution for extreme industrial wear and tear. You are utilizing a system that simply refuses to degrade under the rugged reality of daily industrial abuse.
Okay, so the hardware survives the environment, and it does so safely without a cage. Now we have to look at the actual output. Let's pivot from the environment these machines endure to the physical execution of the tasks they're actually assigned.
And this brings us back to the origins of clinical technology. Consider the rigorous demands of pharmaceutical compounding.
Right, making the drugs.
Yeah. When you are formulating a medication, microscopic accuracy is a strict regulatory requirement. You are dealing with fluid dispensing or micropipetting, where a deviation of just a fraction of a millimeter can alter the efficacy of a drug.
Which could potentially harm a patient.
Exactly. The robotic arms engineered for these environments operate with kinematically perfect repeatability. They utilize high-resolution optical encoders at every single axis.
So they always know exactly where they are.
Thousands of times a second, they are reading positional data to ensure the end effector lands in the exact same microscopic coordinate every single time.
Yeah.
It is absolute mathematical perfection.
Here's where it gets really interesting for anyone managing a standard production line. You take that medical grade kinematic repeatability, that microscopic accuracy, and you drop it into general assembly,
Right.
or you apply it to packaging or electronics manufacturing. You are no longer just automating a task, you are injecting an entirely different class of precision into everyday workflows.
If we connect this to the bigger picture, the standard of quality control shifts from just acceptable tolerance to absolute uniformity.
Which is huge.
Our sources point out very specific applications for this. Think about precision sorting of fragile components, intricate kitting of mixed product bundles, or really delicate part positioning.
Things human hands might fumble.
Exactly. When you apply clinical-level optical encoders and micro-precision to these tasks, they are executed with flawless mathematical consistency that standard pneumatic cylinders or basic stepper motors simply cannot achieve.
We're basically taking out the Monday morning or Friday afternoon human slump.
Oh, for sure.
The robot doesn't get tired or make a millimeter mistake. If a microscopic ribbon cable needs to be inserted into a circuit board housing, or a specific assortment of medical devices needs to be kitted into a specialized blister pack, it happens perfectly. The first hour of the shift looks exactly like the 1,000th hour of operation.
And the ripple effect of that consistency fundamentally alters a company's bottom line. By integrating surgical precision into everyday tasks, you essentially eliminate the physical human margin of error.
Which saves so much money.
For a manufacturer, that translates to a drastic reduction in material waste. You're looking at a sharp drop in rejected parts and scrap material.
Plus, it really cuts down on the labor hours required for quality assurance checks on the back end, right?
Yeah, because you are guaranteeing a near-perfect standard of quality right at the point of origin. High-tech, certified automation is no longer a luxury reserved exclusively for scientists and surgeons. It is the new competitive baseline.
It really redefines what it means to build a resilient operation. I mean, if your competitor is utilizing a system with fenceless clinical-grade precision and your traditional assembly line is still drifting a few millimeters out of alignment every 100 cycles, well, you are eventually going to bleed revenue through waste and downtime.
You just can't compete with that level of uniformity.
Bringing this surgical-level precision, inherent fenceless safety, and laboratory hygiene to the general factory floor is not just a clever workaround for a tricky layout. It is a fundamental strategy for future-proofing a business.
It really is.
It allows you to maximize your facility square footage, survive the harshest industrial washdowns without hardware degradation, and execute every single task with mathematical perfection.
Which is the dream for any plant manager.
Exactly. And for you, listening right now, if you are looking at your own shop floor and wondering how to eliminate physical bottlenecks while elevating your quality control to a clinical standard, the next step is right in front of you.
Take the leap.
Connect with the experts at Triple Automation by visiting tripleautomation.com. It is the most effective way to start transforming your operations today.
You know, the implications of this crossover are profound, and they really leave us with a lingering question about the evolution of manufacturing.
Ooh, what's that?
If everyday factories are adopting surgical-level precision and flawless mathematical consistency today, what happens to our perception of quality tomorrow? In a few years, will the human touch in manufacturing be seen as a premium feature or simply a guarantee of imperfection?
Man, that is an incredibly compelling thought to leave on. Thank you for joining us on this deep dive. Keep examining the world around you, keep pushing the baseline, and we will catch you on the next one.